Okay, so the good news is I'm not gonna teach you guys how to read or write assembly. Like not thoroughly. I did that last year. I realized it wasn't a good idea because a lot of people get lost really easily. So we're not gonna be doing an assembly crash course. The bad news is we still need to look at assembly, right? So you're gonna learn to mostly read assembly at a very, very high level. Uh, and hopefully things make sense. Okay, so first and foremost, executables. So we looked at executables a bit earlier, right? When we were looking at detected easy, when we were looking at the magic bytes. So, okay, to an end user, right? Most people just think of programs or executables as something you double click or you run in the terminal and the computer just does it, right? Because I mean that's the sort of frictionless experience that we produce by developing operating systems. Now the thing is, every operating system has its own native executable format. We touched on this earlier, right? You couldn't run the Linux executable on Windows, and you can't expect to run Windows or Linux executables natively on Mac. That's why the Mac users had to install a Windows VM so that they could actually, run stuff in the VM, like run Windows applications. So even though the underlying source code that might produce the program is the same, it has to be packaged in different ways for different operating systems to understand to run it, right? So, okay, we touched on this earlier as well, compiled and interpret languages. So interpret languages in general is more cross-platform because as long as you have the interpreter on the target operating system, you can run the same script. But compiled languages, right? Compiled languages is when you take source code and then you turn it into machine code. So machine code is the ones and zeros, the bytes that the CPU on your computer actually understands, right? So it usually doesn't contain the original source code. As stated, right, every native executable format is usually platform and architecture specific. By platform specific, we mean Windows takes exe files, right? The proper term for it, like the actual term in documentation, is portable executable, right, or PE. So 32-bit PE files are called PE32, and because they are so creative, right, 64-bit PE files are called PE32 plus, and not PE64 for some reason. I don't know why. This was Microsoft's decision to make. On Linux, we call them ELF files, executable and Lincoln format. And for Mac, they're called Mark O. No idea why. I didn't Google it. Um, the other thing is the instruction set architecture. So most of you guys running Windows on your laptops, you guys are running a x86-64 architecture or AMD 64, right? If you are using a Mac, a modern Mac that uses Apple Silicon, you are almost definitely running an ARM system, right? And Mac in particular has its own custom ARM instructions as well. So you can't expect Mac applications to run on any ARM device. Um, a lot of embedded systems, so like routers or small smart devices, use reduced instruction sets or RISCs. So this is why you can't run an old Mac application on a new Mac without this thing called Rosetta, right, which helps to convert x86 into ARM, right? And this is why even though the underlying like logic for ELF files is actually the same between Mac and Linux, you cannot run x86 Linux ELF files on Mac natively anymore. Okay, so what we're gonna do, because these are easier, right, in structure actually, we're gonna look at ELF files, right, primarily. And next week, when we're gonna do our big decompilation exercise, we are going to look at a piece of ELF malware rather than a Windows exe file. This is very deliberate. It's because Windows exes are way, way more complicated and have a lot more protections in place. So the first thing that we're going to consider is the ELF header. So we saw the ELF magic earlier, right? The ELF at the start of the ELF file, but that isn't the only part of the header, right? So it has ELF at the start, but then it's followed up by some metadata that tells the Linux operating system where code and where data in the ELF file is positioned. So in this graphical representation, right, you can see the ELF header, then the program header table. So each section of the ELF file has its own name, right? And each section contains different parts of the ELF file. So this is a bit hard to think of in the head, right? We're going to look at this practically later. So these various sections, you can really just think of them as like chapters in a book, right? Each chapter, each section of the ELF file holds certain data, and there are conventions to this, right? For example, RO data, which stands for read-only data, has read-only data, right? The .text section. So those who did Pwn yesterday, right? When you guys were looking at your functions in GDB, almost 100% on 1,000%, you were looking at instructions that were lying in the .text section, right? If you guys haven't touched stack pivoting yet, I think, but if you guys do any stack pivot, I think one of the take-home exercises is stack pivoting, then you guys might be exposed to the BSS section as well, right? Which is a large section of memory with uninitialized variable space there, right? And .rsrc, which is short for resource, right? So this is where larger resources like images, maybe some text, maybe some audio, right? If it's baked into the executable, it will be in the resource section. Now, mind you, these are conventions, right? An ELF file doesn't need to put executable content in .text. It just needs to put it in a section that the OS knows is executable, right? So you can change the names, and it doesn't change anything about the execution, right? It just changes the way that it's passed. So we're going to use detected easy to help us here, right? So I'm going to reopen. So we've got detected easy here, right? And I want everyone to go to the in the examples like folder, right? The decompilation and then ELF examples. And then you should see a file called stager. So I want you to drag and drop stager into detected easy. So if everyone has managed to put it into detected easy, what I want you guys to do next is to click advanced. And then you should see a whole bunch of buttons pop up, right? Okay, everyone can see this now? Oh, it's huge. Awesome. Okay. So what you guys should be able to see, right, in this table, is you should be able to see the names of all the different ELF sections that are available. And when you like click any of them, right, the hex dump that it shows at the bottom are the corresponding bytes. So for example, at the very top, there's no section here. This is the header. This is the ELF header. So that's why you see the ELF bytes, right? But as you start going down, you can see some sections are very short, some sections are very long, right? So for example, in the .text section, this is where all the machine code, the assembly that makes up the program is, okay? Those who took Pwn, can you tell me what the PLT section is? Or was that not covered yesterday? Wasn't covered, okay. Procedure linkage table. If you go over to .ro data, right, this is read-only data, and you can see there's some strings here, right? chmod, execve, temp stage bin, stager, right? So you should be able to see some strings, and these strings are all stored in the RO data section, right? Everyone can see this? Yeah. Then you can see there's a staged payload. So this is a section inside the ELF that contains another ELF. So we'll actually analyze this next week, right? But for now, just know that we've got an ELF and an ELF. So some of the other sections, you can see a lot of the metadata that we were talking about earlier, right? For example, in BSS, BSS contains a string telling us the GCC or the compiler version that was used to create this file, right? Same goes in comment. Interp, the interp section tells us the path to the linker that it's expecting, right? And then there's a whole bunch of other strings here, right? Dynamic strings, the GNU version. Those who took Pwn yesterday, did they tell you all what the GOT is? Also no, global offset table. Okay, so yeah, these are the sections in an ELF file, right? The most important one that we'll be looking at today, as mentioned, will be the .text section. Because the .text section is where the code, the actual machine code of the program exists. Okay, if there's any takeaway from this brief little excursion, right, is that the ELF header contains information about the sections in an ELF file. There's a table there, and these sections contain different parts of the file, And the .text section in particular is the most important because the machine code of the program is there. So the actual instructions that the CPU is running are all found in the .text section. Everyone got it? Okay. All right. So like we said, where's the code, right? Because the thing is, if we look at the .text section that we were looking at just now, this isn't source code, you know, this isn't readable C, this isn't Python, this isn't anything that we as humans can read, right? This, to a computer, is machine code, right, that the CPU is actually reading. We can turn this into assembly, right? But assembly isn't super easy to read either, right? Although we will be reading a bit later. But yeah, how can we analyze this? Because there's just no way that reverse engineers are just staring at raw bytes the whole time, right? So this is where we move on to decompilation. Decompilation requires us to first discuss levels of abstraction. Now, this lost a lot of people yesterday, so I'm gonna try and do the explanation slowly. And if anyone doesn't get it, I will try my best to re-explain it. Okay? So like onions, things have layers, right? Where's that quote from? Like Shrek? It's from Shrek, right? Okay, so yes, we're gonna understand the layers and levels of abstraction that computers operate in. So uh, at the very lowest level, and by low level, I don't mean easy, right? When we talk about like high level and low level, right, it's not about difficulty. It's about how close we are to the silicon, okay? That being what's on the CPU. So the CPU, like if you tear open a CPU, right, it's not even looking at ones and zeros. It's working with electrons. Like it's literally working with physical electrons on silicon atoms, right? That's the absolute lowest level of abstraction, right? If you go up one, then we start talking about binary. We start talking about ones and zeros, right? Binary encodes this thing called machine code, right? And machine code, so if your ones and zeros are in a specific order, then the CPU knows, okay, 1010 tells me I need to add the next two numbers together. So I'm gonna read 0001111, gonna add it with 1111000, right? So somewhere on the chip, it manages to understand that that's what it has to do. So far, so good. So binary is the lowest practical level of abstraction, right? And then one higher is machine code. So when we talk about abstraction, this is a matter of granularity or detail, right? Ones and zeros are a lot of detail, but not very human readable, right? Source code to a computer is less detailed, but to us is more readable. I know this seems counterintuitive, but hopefully it'll make sense later, right? So an analogy that hopefully will help to tie this over later. When you give someone an instruction, you can give them an abstract instruction like get from home to school, you know, like this. If you just tell someone get from home to school without giving them further instructions, right, there's so many different ways that they can approach it. This is the highest level of abstraction, right? This is the command in general. You go down one level and it's a bit more detailed, it's a bit more granular, right? Take the MRT from home to school, be a bit more detailed with it. Walk out from your home to MRT station A, board the train, exit at MRT station B, walk to school, right? This is a bit more granular, right? We're gonna see one-to-one how this corresponds later. And then at the lowest level with a lot of granularity, you're giving them precise instructions on how to move their limbs and do all this blah, right? Okay, so hopefully that forms the basis for what we're gonna look at next. Recall what we were looking at earlier when I was telling you guys about data representations, right? A string. So a string in Python or a string in any programming language for that matter, when we do this as a string with your quotation marks, that is a high level of abstraction, right? But if you go down one, in actuality, it's not, the computer doesn't think of a sentence as a sentence. It thinks of it as a collection of characters, right? So to a computer, this is a string, is the letter T, the letter H, the letter I, so on and so forth, in a list. So far, so good? Everyone following? So you see that's a bit more detailed, right, in terms of what the computer is actually interpreting. Go down one more level, and then each character is corresponding to some number from the ASCII table, right? So T is 0x74, H is 0x68, so on and so forth. So to a computer, down one level of abstraction, it's not a collection of letters because the computer doesn't know what a letter is. It doesn't know the alphabet, right? What it knows is numbers. So a string is a collection of characters, which is actually a collection of numbers. And that collection of numbers to a computer is just a collection of ones and zeros. So far, so good? Everyone able to follow? Okay. Now let's look at code. High level of abstraction is the code that you type. So let's say in Python, you define a function. I'm going to define add numbers to add two numbers together with the constant 10. This is our high level of abstraction when we type it into a Python script or the Python interpreter. Go down one level of abstraction, and this is what Python actually works with under the hood. Right? When you write a Python command or like a Python script, Python compiles it down to its equivalent of assembly. This is Python bytecode, right? So assembly, in a sense, okay? And all assembly or all bytecode is also just a bunch of numbers in a specific order. And all numbers that are in a specific order, it's actually just binary, right? Are we following so far? This one can get. Okay. So at the top level of abstraction is the source code. At a lower level of abstraction is the machine code. What gets you from source code to machine code is a program called the compiler, right? So when you write your source code in C, and then you convert it into your L file that contains machine code, your C code was processed by a compiler, usually GCC, and then it produces the machine code. So far, so good? Okay. Ken? Okay. A bit tired, like it's been a long day of content. Okay. In between source code and machine code, we actually have other layers of abstraction. We have intermediate representations, right? You all don't need to know what this is really, right? And then assembly. Even though to us assembly might seem like scary, granular machine code already, it's actually an abstraction of machine code because machine code is the bytes that the CPU is interpreting. When we give it a name, right, it's assembly, right? And that the fact that we can give it a name means we've gone up a level of abstraction. And at the very lowest point is pure binary. So, as mentioned, source code is often the highest level of abstraction that we operate on, right? When source code is interpreted or compiled, we go down the levels of abstraction until we reach something the computer can actually interpret, which is machine code, right? As a pop quiz bonus question, can you guys think of a level of abstraction even higher than source code? Like code like this. Pseudocode? Okay, that's a good answer. Someone else? Scratch. That's a very good answer. Any code blocks? Yes. There's an esoteric answer as well. Okay, so yes, code blocks, Scratch, things like that. That is a higher level of abstraction than source code. Right? If you've ever done Lego robotics, right? Same goes. Lego Mindstorms. It's also block programming. So notice how block programming you don't have to like type code actually, right? Because your if statements, your variables have been turned into blocks, and that's an even higher level of abstraction. Um, a very good answer that I got yesterday, which was also the thing that I was thinking of when I made the slide. When you tell an LLM to write code for you, that's an even higher level of abstraction, right? Because you've now gone from source code to natural language, right? Instead of having to type for I in range 10, print hello, you just type print hello 10 times, right? And then the LLM makes the code for you, you know? So like that's an even higher level of abstraction than source code. So like the reason why I'm bringing this up is so that you guys can really solidify your understanding of abstraction, right? Assembly, right, is when we go way down, right? So it's a way that we're abstracting machine code or binary into something that's readable, but still close to what the CPU is actually doing, right? So we'll see that later. And again, everything that's being run and executed by the CPU has to be in a language that it understands. So for most of us, that language is x86 64, right? that instruction set, the architecture, right? For Mac users, it's ARM. So ARM instructions and x86 instructions are different. I realized I glossed over the definition of instruction. An instruction is just a fragment or machine code which does a specific action, right? So if you put multiple instructions in a row, then it will form a bunch of actions in a row, right? Like code, like logically, right? So this is just as a tidbit, right? If you tear open a CPU, this is what it's operating on. So yesterday, if you guys did pwn, right, those registers that you were moving around, so your RAX, your RBX, they are physical silicon, right? There are physical lanes inside the CPU where your RAX, RBX, RCX is storing data, right? Whenever it does add operation, minus operation, right, it's being handled by the ALU, which is the arithmetic logic unit in the CPU. Okay, this is all spurious additional information. This is not critical to understanding the content later, but I feel like it's good to know, right? And if you ever want to study computer organization or computer architectures in university, right, this is something that they will cover, right? So microcode even. So like the CPU itself has its own instructions and manages besides assembly, right? And it's baked into the CPU in silicon, right? And yesterday, if you were, I don't know if they mentioned anything about flags. So like zero flag. Okay, no. Like flags are also managed by silicon here. So the way that you get this is literally by taking a CPU, removing the top, and then burning off a lot of the stuff with chemicals, and then you can see the raw silicon traces. So yeah, um, in really, really advanced security research, so like well beyond stuff that like I'm doing, right? People are analyzing CPUs at this level. So again, as mentioned, so that tangent aside, right? Um, the process of translating source code into machine code is called compilation. So I'm gonna bring up this website called Godbolt, and I'm gonna let you guys look at some code examples, right, which will show you how C source code gets turned into assembly. Okay. Yeah. So compiler explorer, right? Lots of exploring today. We did registry exploring. Now we're doing compiler exploring. Okay. So this website, like I said, on the left, you can input source code, and on the right, it will show you the output assembly. So what I'm gonna do, I've got some examples that I want to cover. I'm gonna copy them over. For you guys, right? We've put this in the Godbolt folder, so 1234.c. So if you want to paste this in like on your own computer rather than looking at my screen, you can do that. You can go ahead, right? But I'm just gonna copy it over myself, and then we're gonna look at it together. So the first example that we're gonna look at is very simple, right? It's just a C program that prints hello. So even if you can't read C, I hope that this program is simple enough for you guys to understand. Yes. And then on the right is the output assembly. So something really cool that Godbolt can do, when you highlight the assembly on the right, like when you hover over the assembly on the right, it will highlight on the left what the corresponding C code was supposed to be. So for example here, right, call printf in assembly, the instruction that happens in assembly is called call. And then printf is the function that it's calling, right? And you can see over here when I hover over it, it corresponds to printf over here. So I think those that did pwn would have seen this yesterday, like call, right? Then over at the bottom, move EAX0. So moving the number 0 into the register EAX, right, corresponds to this constant 0 inside the original code. And then the return corresponds to pop RBP and ret. These two is what the original return statement inside C got turned into an assembly. So some other things that we can notice, right? For example, the hello string is a global variable in this program. And this is reflected in the assembly as well. In the assembly, it puts it as a global variable. Does this make sense to everyone? So this brings us to example number 2. which is almost identical. So it's identical in function, but it's different in layout. Notice that I've taken hello and I've turned it into a local variable, right? And now the string hello is no longer global. Instead, it's been encoded into numbers. Because remember, a string is just a collection of characters, and the characters are just numbers, and numbers are just numbers, right? So that means that these numbers actually encode the string hello. And that is what the CPU is using when it prints it out later. So far so good? Does make sense to everyone? Okay. Another one. So this is a simple XOR decrypt, right? You don't need to understand all the instructions. I just want you to see that things like the XOR operation have a corresponding XOR instruction in assembly, right? And sometimes the compiler, the compiler can make decisions on its own. So for example here, every time we do printf, right, we only print one character. Well, printf can support printing more than one character, right? Printf can print strings. But since it's only printing one character, the compiler made a decision to optimize it, so make it a bit faster by replacing printf with putchar. So that means it only prints one character. Like putchar is a dedicated function to printing only one character at a time. So yeah, you can see calls to other functions being done like this, call string length, call putchar, right? Things like your comparison. See, like this comparison in the for loop, there's a comparison function inside the assembly. Yeah, I get this part is a bit dry and it's a bit hard to understand if you're not used to C and assembly, right? Unfortunately, it is part and parcel of reverse engineering. Yeah. So again, like if we look at example number 4, we can see that different functions can get put in different locations in assembly, right? And we can do like call check, which is the function that we have defined. This is the check function, right? And again, we can see some interesting optimizations. For example, over here, checking if a string length is equal to 0. Notice that it doesn't have to call string length. Because if you remember what I said as a throwaway comment a few hours ago, right? Strings are terminated with 0 in most programs, right? So a different way to check whether a string length is 0 is just to check whether the first byte is 0. So this is what it has been optimized to in assembly. So it doesn't even have to call string length. Okay, like I said, this is all a bit confusing. This is all a bit hard to pass in first try. I do recommend that you guys go home and experiment with this on your own and see and try and understand a bit of the assembly output. Right. This is the level of detail that I'll go into today for now. So everyone managed to get it? Okay. So what we were doing there, right, was alternating between the levels of abstraction. We were going between source code and assembly, right? But as mentioned earlier, right, where I need to see my OBS. As mentioned earlier, compilation goes down the levels of abstraction. We went from high-level source code down to low-level machine code. What we want to accomplish is the reverse. We want to get machine code and we want it to turn into high-level source code. Because like we said, in the context of malware analysis, right? Malware is usually compiled exes, compiled ELF files, right? And the ELF files have their instructions in machine code in the .text section, but they're not source code. If we want to analyze it, we want to have some sort of source code to read. So again, it's the act of taking compiled output and trying to produce a representative source code. Now this process is very complicated, right? But really smart people have come up with really good programs for us to be able to do this. So for example, this is the output in one of those programs. On the left is the raw disassembly. So these are the raw assembly instructions that are inside the .text section of a program. And on the right is the pseudocode output of the decompiler. So notice how it's just like Godbolt, but we've flipped it around, you know? Instead of taking source code and turning it into assembly, we're taking assembly and trying to turn it into source code. So far, so good? Everything tracks? Okay. And the thing is, the output of decompilation isn't necessarily interpretable or like compilable source code either. It is an approximation, right? It's pseudocode. but it tries its best. So I'm gonna do something interesting, right? We're gonna stop looking at assembly, or like exes and elfs for a moment. We're gonna look at something that we are more familiar with, which is Python. Okay. So something that I'm gonna do. So you guys don't have this example, unfortunately, because I updated it last night. But I'm still gonna show it to you all. So eyes on the screen, I guess, right? What I have here is a Python script called race.py. So this is a very simple script. I'm gonna open it in VS Code. Race.py. Hey, enter your name. Can we get a trainer name? Someone just threw out a name. Liang Wei. Ooh, much to think about. Okay. And yeah, so it's just a very simple Python program, right? It's racing horses. Who's gonna win? Who's gonna win? Oh, okay. Awesome. So in the case of Python, instead of forcing the Python interpreter to have to understand your Python script every time it runs it, if your Python script is not changing, right, all it will do is it will compile a version of the Python script into bytes. And then it will use this compiled version and run it. So what I have here, race.pyc, if we go over the hex edit, hxd, sorry. If we go over the hxd and drop it in, you'll notice that this is not this is not Python source code. Like this is not a .py that you can read. These are bytes, right? And these actually encode Python assembly that the Python interpreter understands. So if we do Python and then race.pyc, oh, okay, there we go. So I can run the same program and it does the same thing, right? Who's gonna win this time? Wow. Okay. Anyways, so you see it's the same program, but it's in a different format, right? Python bytecode versus Python script. And notice just now I had an issue running it where it said bad magic number, right? The Python bytecode is specific to the Python version as well, right? My current Python version, now that I am using my venv, I think this is the command. The current Python version I'm looking at is 3.11, right? But if I go out of my venv and then I look at the Python version of my system, it's 3.14. So things that were compiled in one Python version won't even work with other versions of Python, right? So bringing back some of the concepts we had earlier, you can think of this as CPUs with different architectures, right? They have different sets of instructions, and one CPU might not understand a CPU like another CPU's instructions, right? In fact, like this even applies to the same architecture. If you look at x86 processors, right? Processors from the 90s cannot run some code that was written in like nowadays, right? Because it's not just their chips are less powerful, they don't have the silicon that produces some of the instructions that we use today. So like in a lot of video games, there's a lot of 3D graphics, right? So to handle 3D graphics, there's a specific set of instructions that performs vector calculations very fast. You don't need to know what vectors are, but it's basically just a certain set of math operations that go that are really complex, right? And nowadays CPUs, they have specific instructions to handle those math operations. Older CPUs don't. Okay, that was a bit of a tangent. Let's go back to the Python. So what I'm gonna do now, I have written a script. I have written a script that disassembles the Python compiled, the PYC bytecode. So let me reactivate my venv. I'm gonna disassemble race.pyc. And you can see here, this is the Python assembly, right? This is the bytecode that makes up the compiled Python program. So far, so good? Question mark. Any part of this a bit unclear? So what I want you to notice about the output here, I'm going to try and scroll to the top. So you can see some patterns inside the assembly. For example, at the top of the original race.py script, let me try and find the do I not have it open right now? I don't. Okay. if we look at the original race.py script, at the top I import random, I import time, I import OS. Then when you look at the Python assembly, the Python bytecode, you can see it does the instructions import name, store name, import name, store name, import name, store name, right? Those are my 3 imports at the start, turned into assembly. And then it builds lists. Build list, and he guesses what it does. Builds a list. Awesome. Anyone want to guess what load const does? Loads a constant. Very good, right? Compare op. Comparator. In this case, equal, right? Return value. Returns a value. Yeah, so you can see this is readable, right? If you spent really long looking at it, maybe you could analyze it to a sufficient degree that you could understand what the program is doing, right? But this is still a bit intractable, right? Assembly is not easy to read, and it's not human friendly. What we want to try to get is something that looks like the original Python source code, right? So what some really smart people have done is, so notice just now what I was saying, right? A lot of these assembly instructions turn into patterns that we can recognize. So for example, load const, import name, store name is the pattern that does import module. And we see it repeated 3 times, right? So what if we have a program that every time it sees load const, import name, store name, it knows, oh, okay, the original source code was import name, right? So that program exists, right? Let me clear the thing. There's a program called I.YCEP. So the other name for it is decompile. So it's the same thing. This is decompile, right, or I.YCEP. It is a decompiler for Python bytecode. So for example, if I do, I have it on hand, right? I.YCEP.exe, and then I'm going to pass in and be very observant here, right? I'm passing in the PYC. I'm not passing in the Python script, okay? So I'm passing in the raw bytes that makes up the Python bytecode, the Python assembly, into this program. And what this program gives me at the end of it, oh, whoops. Race, yes, my bad. What it'll give me at the end of it is something that looks like the original source code. And you can see there's some parts which it doesn't know how to handle as well, right? So if you were to just take the output of this and put it into Python, it wouldn't work straight away because there's some parts of it that it doesn't understand. But it does a pretty good job at reconstructing most of the program, right? And you can very clearly see that this isn't a one-to-one equivalent of the original script that we had, right? It's an approximation of it, but it's a really good approximation of it, right? So you can see all sorts of weird artifacts. Block stack is not empty, right? Return none. If we go back to here, you can see my draw function doesn't return anything, right? But I.YCEP decided to make it return none. So this is a side effect of the fact that it's trying to reconstruct the Python code. And actually, if you were to copy this section, something I want you guys to notice as well. So like, oh, whoops, ow. So if we were to copy this function and paste it into VS Code so that it's a bit cleaner to see, and then let's remove this. Again, notice that I.YCEP put a return none inside the for loop. So you guys tried to copy the code that came out of here and paste it into Python, it wouldn't even run properly because it would stop halfway through, right? This is a side effect of decompilation. Decompilation is not precise because we are doing a recovery process, right? We're trying to bring back the source code from where there is none. Does this compute for everyone? Does this make sense? Okay. Yeah.
How's the variable names recovered during?
So that's a very good question. So remember what we were talking about for a big part of this morning? Metadata, right? And remember how metadata can inform programs and can inform us information about the programs itself. Python is very special in the sense that its assembly has metadata embedded in it. Yeah, so notice how when I did the disassembly initially, right? when I did the disassembly, on some of the lines of assembly on the side, it has the text, right? It has the name of the variable over there. So it helped us to map back that this is the username variable. Or it helped us to map back this is the positions variable. So this is a specific quirk of Python, right? You won't see this in a lot of other languages. Another language which does retain some metadata is Java, right? When you make jar files with Java, it retains some of the metadata, which lets you reconstruct the variable names. This is why it's so easy to mod Minecraft, right? This also applies to .NET, which you guys should now all have installed on your computer because you have to install Registry Explorer, right? An example of a program that rarely keeps the metadata of the function names or the variables would be C, right? Once you compile it down, there's no reason for it to keep it, right? Although I think if you guys were doing Pwn yesterday, did you guys do red to win? In GDB, did Nicola make you guys do like info address main? No. Info function. Okay. Yeah, so and notice how info function tells you the address of the main function and the win function, right? How did GDB know that that function is called main and that function is called win? You ever think about that? Ah, there's metadata baked into the L file as well. Yeah. So you can deliberately include metadata if you want. In fact, when we are producing programs, right, we make what's called debug builds. Debug builds come with so much metadata that you can correspond the assembly instructions directly to the original lines of source code, right? Which is very helpful when you're looking for bugs. Anyways, so decompilation. We're gonna learn how to set up a decompiler, and we're gonna start with some very, very basic examples, right? I actually hope that we can wrap up before 6, and then I can open the floor to more questions rather than just trying to force fit a bunch of stuff. Okay. So these are softwares that exist which help us to perform decompilation. The one that I got you guys to install is Ghidra, right? Right after this, I'm gonna make our dear assistants make sure that you guys have Ghidra installed properly, right? Uh, in the industry, right? In the industry, a lot of us use IDA, which is short for Interactive Disassembler, right? And Binary Ninja. Now, the reason why we're not using these is because these are paid. Something quite cool that exists is this thing called Binja.cloud. Oh wait, whoops! It's supposed to be like Binary Ninja Cloud, I think. Let me search it up properly. Yeah, cloud.binary.ninja. Ah, there we go. So let me see if I can log in. I don't. Oh, I did. Okay, so just something cool to let you guys see, right? And this is something that you guys can explore and use at your own time. So I made you guys install Ghidra, right? And you guys all have Ghidra, right? Right? Okay, the thing is, Ghidra is one of many decompilation softwares that exist. Binary Ninja is another one. Binary Ninja has a free cloud version that you can use online. So just as a very short anecdotal story, 2 years ago, I was stuck on Pulau Tekong, right? Because I was doing my basic military training. And what happened was the DSTA CDDC CTF was playing, right? And I needed my Team Slight Smile, to qualify. So I did my rev challenges on my phone on Binja Cloud, and it worked. So you can see these sessions are from 2 years ago. These are the challenges that I was doing on my phone, right? If we take a look, wait, that's crazy. Okay, so this is a decompiler. This is an example of a decompiler that you can use, Binja Cloud, right? Binja has a lot of really interesting features like this. This is graph view. So we will not be doing this in Ghidra because it's a bit advanced, right? But I just want to let you guys see this as like a tidbit of information, right? You can imagine your programs as giant blocks, right? And each if statement is like a branch that goes to a different block. And something that we commonly do in reverse engineering is we look at graph views so that we can literally trace the flow of a program, right? So something else that's really cool. So I'm gonna switch over to code view and then look at the main function. So something else that's really cool that Binja provides, which corresponds very directly to something that I was teaching just now, right? Is different levels of abstraction. So if I need to look really closely to try and find it. Okay. So Binja can show me my program in raw assembly, right? So this is the assembly that makes up the program. And then it can show me one level of abstraction higher. So this is a slightly higher level of abstraction, but not still very close to assembly. But notice that now it's introduced like equal signs, function calls, and it's turned my arithmetic, so like my minus and plus operations, into actual minus and plus operations, right? Then I can go up one more level of abstraction, and then it starts to structure things a bit more, right? Keep going higher and higher until eventually it gives me code that looks close to C. And you see, this is very similar to like the original source code of a program. So this is what we're going to be doing in Ghidra as well, right? We're going to be taking assembly and we're going to be turning it into pseudo C, right? Or something close to C, not exactly C, but readable code nonetheless. So first thing that I want you guys to do, yeah, the next slide is just telling you that we're gonna do ELF1. So everyone should have extracted Ghidra to its own folder. I am stressing this point because last year I had a lot of people that were trying to run Ghidra from inside the zip file. That doesn't work. Okay. Yeah. And you guys should be able to just run Ghidra run.bat. Okay, so now that everyone has managed to make it to this screen, right, we're going to make a new Ghidra project. So we're going to go File. Okay, we're going to go File, New Project. Make sure it's non-shared. We're not making a shared project, non-shared, right? And then you can just pick the I.YCEP directory. So I mean, right now it's just in my standard Scratchpad. Wow, you can see all the CTFs I played. And then you go here, I guess. I'm gonna make a new folder actually. Let's go call it Ghidra. And then you can name the project whatever you want. I'm gonna name it I.YCEP. Finish. And then just press finish, and you should get something that looks like this. It should say I.YCEP over here. It should say I.YCEP on top. All right. Okay. What we're gonna do now? So like since most of us managed to get it done, right? We're gonna drop in a file for Ghidra to analyze. So I want you guys to go to your examples folder. And then I want you guys to go to decompilation. Then I want you guys to go to ELF examples. And then DST. So you should see 3 files here. Okay. So these 3 files are all Linux executables. So I'm just going to run them so that you guys can see what they do and get a feel for what the programs are supposed to do. So this is just a tip and trick. So if you guys do end up playing CTFs and you guys do reverse engineering challenges during CTFs, do not just jump straight into static analysis of programs. It is usually important to know what the program is doing first before you even want to start on analysis, right? Because if you just look at the code straight away, you might miss some points, right? Anyways, so let's see what the first one does. So everyone should try this, right? Open a Linux shell inside the ELF examples. The first program should print the time. So the first binary should print the time. The second binary should be a very interesting program.
Guys, I got problems because we got Singaporean DeepSeek.
Why should we ask Singaporean DeepSeek?
Hello. Hello? Okay, hello.
What?
Type in the word heap.
Creep.
Free.
Aww.
Aww. I'm gonna like your pro.
Okay, so that's Singaporean DeepSeek. That's the second program that we'll be looking at. Okay, that's program number 2. And then program number 3. Program number 3 should drop turtle.jpg in your current working directory. So these are the 3 programs that we're going to use to ease you guys into decompilation for today. Because it's been a long day and I don't want to overload you guys, we're just going to look at the first one, okay? The first one, the simplest one, the one that just prints the time, okay? So what you guys can do is you can just take the first binary, drag and drop it into the Ghidra window, and it should import it. So you should see a prompt like this, and note that Ghidra automatically identified this to be an ELF file, and also that it's an x86-64 ELF file in particular, right? And then just press OK. So it's going to come up with a whole analysis report, right? You don't need to read all of this, but you can see some of the metadata that it managed to extract from the file when it imported it. So just hit OK, and then double click on the file name. The dragon should pop up, and then this will start the decompilation process. So say yes, you want to analyze now, and then press analyze, and then it should start doing the analysis of the program. Okay, so everybody should be able to see a program that looks sort of like this, right? It might not be showing you, is it showing you main immediately or no? No, okay. I'll show you how to get there. I do want you to learn to navigate the program first before we do anything. Okay, first and foremost, in the top left, I want you guys to notice that the sections, right? So remember earlier we were looking at ELF sections, right? All these sections that are defined inside the program are split up here. So if you double click on any of these, inside this view, the this assembly listing, it will jump to the section that it corresponds to, right? So for example, if we go to the I can't, oh, it's so small. Oh, it's so small. I can't see it from here. Okay. Well, you can just click around and just play around with this to see what sections there are. See, for example, this is the .interp section. This is the .note GNU build ID section, right? If you go all the way to the top, right? This is the ELF header, right? So you can see in Ghidra what it gives you is the hex dump and at times alternate representation of it. Everyone managed to click through the sections? So remember what I said earlier, what section contains the machine code? Let's stick in anyone's mind. Text, dot text. So, oh, my eyesight is so bad. Dot text should be somewhere. There, go over it. Dot funny here. Okay. Awesome. So this is dot text, right? And if you look in Ghidra, the start of dot text, and if you double click on the word start here, it should show you the decompilation of the start function on the right. Does everyone see something that looks like this? Yes? So this is the entry point of the ELF file. So even though we know it's the main function, right? The main function doesn't start at main. I don't know if this was covered in Pwn. Maybe? Underscore start is where the program actually starts from, right? And we can see the main function. So let's double click on the main function together. And this is the main function. This is the decompilation output of the main function. So if we go back into GDB, I'm just gonna run until it actually goes to main. You can see the first few instructions of main here: push RBP, move RBP, RSP, sub RSP, etc. Right? You can see that in the decompilation listing of Ghidra as well. You should see push RBP, move RBP, RSP, sub RSP, move EDI, and then call the time. Right? This is exactly what you'd see inside the program when you're running it. And this is the abstracted, lifted version of the assembly into pseudo C. So if I highlight this line, you can see this is the assembly that it corresponds to, right? Call time. And this is call to C time, and this is the printf. And I want you guys to notice one more thing. The variable names are missing, right? Because there's no metadata about the variable names. But there's metadata about the function name. That's why we know that this is function main, right? And something that you can do in Ghidra is you can rename variables. So right now, it's not so helpful to have a variable called local_10. Good job, I know it's a local variable, right? If you highlight it, so if you just click it, you'll highlight it, right? Then press L. Then it'll let you rename the variable. So maybe I would call it time_val or something. So you can rename the variable from local10 to time_val, and now the code is a tiny bit more readable, right? So time_val comes from a call to time, and then time_val is passed into ctime. Can someone tell me what ctime does, or Google what ctime does? Yeah, it converts it into a readable form. So what would we call this variable? Readable time. Yeah, I like that one. Readable time. Yeah, so you see, we've managed to make our source code a tiny bit more, well, our decompilation output a tiny bit more readable, and turn it into something that's closer to what real source code will look like, right? And something I want you guys to note again. Remember the PYC example earlier, and how it had all sorts of weird artifacts here and there, and how it had like weird return nones and things that didn't actually appear in the original Python. We actually have the original source code for this program. It's been distributed to you guys as well. If we go over to elf examples and then source and look at first.c, this is the original source code. So you can see the original variable name for time was just t, and there was no second variable for ctime. It's just done in one line like this. But Ghidra doesn't know that. There's no way for Ghidra to know that. So instead, it creates a second local variable, and then it puts it over here. So you can see that's the discrepancies between the true source code and the approximate source code output. You'll see a lot of these tiny artifacts here and there, right? And next week, when we look at our big example, it's gonna get a lot more confusing. So this is it for today.